Tonight, we explore just how hot a star can be. Our nearest example, the Sun, has a surface temperature of about 5,500 degrees Celsius. But that's only the surface. Deep in its core, temperatures rise to around 15 million degrees Celsius, hot enough for nuclear fusion to occur every second. And the Sun is not even among the hottest stars. Across the universe, there are stars far larger and far hotter, pouring unimaginable amounts of energy into space. Every second, the Sun releases more energy than humanity has used in its entire history. This energy radiates outward in all directions, into the emptiness of space. If stars pour so much energy into the universe, what is the temperature of the space between them? Surprisingly, it's about -270 degrees Celsius. That's just 2.7 degrees above absolute zero. This faint warmth doesn't come from stars. It comes from the cosmic microwave background, the leftover glow from the birth of the universe. In other words, the temperature of space is not set by nearby stars, but by ancient radiation from billions of years ago. To understand this mystery, we need to understand how heat moves. Heat travels in three main ways: conduction, convection, and radiation. Conduction happens when particles touch, like a metal spoon heating up in hot tea. Convection happens when fluids move, like warm air rising in a room. But both of these require matter, particles, something to carry the heat. In space, there is almost nothing to touch and nothing to flow. That leaves only one method: radiation. Radiation can travel through empty space as light and electromagnetic waves, but it only heats objects it hits, not the space in between. Space is often described as a vacuum, and that's almost true. Between planets and stars, there are only a few atoms scattered across vast distances. In many regions, you could travel millions of kilometers and never hit a single particle. With so little matter present, there is nothing to absorb heat, nothing to store it, and nothing to pass it along. Heat cannot exist in emptiness by itself. It needs particles to live in, and space has almost none. If space is so cold, why do we feel warm when sunlight hits us here on Earth? The answer is subtle but important. Sunlight does not warm the empty space it travels through. It only warms the objects it strikes. When radiation from the sun reaches Earth, it hits the ground, the oceans, the atmosphere, and those particles absorb the energy. The atoms begin to vibrate faster. That vibration is what we feel as heat. Our air then spreads this warmth through conduction and convection, creating a stable, livable temperature. Now imagine removing the air, removing the oceans, removing everything. The sunlight would still pass by, but there would be nothing there to hold the heat. Imagine floating in open space without a suit. In direct sunlight, radiation from the sun would begin heating the side of your body it touches. But turn into the shadow, and you would start losing heat rapidly. With no air around you, there is no conduction, no convection, nothing to balance the temperature. One side warms, the other side freezes. Space doesn't feel hot or cold by itself. It only changes the temperature of objects exposed to radiation. Here is the key idea that solves the mystery. Temperature is not just how hot something feels. Temperature is the motion of particles, atoms and molecules vibrating and colliding. The more they move, the hotter something is. The less they move, the colder it is. But in space, there are almost no particles to move at all. With nothing there to vibrate, nothing there to collide, space itself cannot hold heat. That is why the universe can contain stars burning at millions of degrees, while the space between them remains just a few degrees above absolute zero. The hottest objects in existence live inside the coldest emptiness imaginable, not because the stars fail to heat space, but because space has almost nothing in it to be heated.